Lunch, so don't want to hold you up too long. Hi everyone, my name is Zac Sweers. I'm an Android developer at Slack based in New York, and today we're going to be talking about builds. Before we get started, I do have a bunch of links in my slides, so I've gone ahead and uploaded them here. If you want to follow along there and be able to check out the links separately, I would encourage you to do that now. Stalling time a little bit longer so people can get a picture of it. All right. So today we're going to be talking about builds. Who here feels comfortable with build systems? All right, so a decent number of people. All right, so I quickly want to cover some non-goals. So one thing that I've always found sort of frustrating with going to builds talks in the past is it's a lot of sort of waxing lyrical about build purity and esoteric concepts, and I don't want to do any of that. I want you to be able to come out of this feeling like you've learned about some things that you're able to grok quickly and take home to your projects immediately. Because it turns out there's a lot of things you can do for your build today that a lot of people don't really know about. Most of this is going to be focused on Gradle, some stuff not Gradle. Anybody here not use Gradle? All right, so nobody from Facebook, Snapchat, or Uber here. So quick Gradle refresher. Most of this will probably look a little bit familiar, but just to cover some core concepts in here. Gradle is a build system made by Gradle Inc. Gradleware? I actually don't remember which one of those it is. But it's made by a company. It consists of tasks, projects, plugins, configurations, configuration, singular, which is different, very important that you know that. Caching and incremental builds, incremental compilation, which are also separate things, daemons, and we'll touch on annotation processing too. So let's start with tasks. Tasks are the smallest unit of work in Gradle. This is a simple task that basically takes an input message, prints it out, writes it to an output file. Tasks work with inputs and outputs. They can have multiple different types, so inputs can be different primitive types, they can be files, they can be lists, maps, what have you. Tasks will usually use files to communicate information to each other across tasks. And these inputs and outputs are also chainable between tasks, and this is what ends up determining, say, parallelization. So say I've got two of these tasks, and the output of one task is used as the input to another. Gradle will take that and say, hey, I need to run this first task first, take its output, chain it into the next one. If there's no dependency between them, then Gradle will say, I can run these theoretically in parallel. Tasks have actions. You just annotate them with this @task action. That's what Gradle uses to know, OK, I'm going to call this whenever it's time for this task to run. This is where you then read in your input values as well. This can also be offloaded to a worker API, but that's not really relevant for this talk. Tasks can be cacheable. So it's an opt-in mechanism. You have to annotate it with this @cacheable task. And basically that means if their inputs snapshot to the same value, you can think of it like a hash, you'll get a cache key hit, and Gradle can reuse that output from a cache entry. If you have a remote cache, that kicks in here as well. This is also a common source of issues, especially if files are involved. So if you have, say, absolute paths being used as your file inputs, and then you run those on two different machines with different paths, you can see where that kind of goes off the rails. These tasks are something that you want to be configuring lazily at configuration time, and we're going to dive into a little bit of that later. And Gradle will then only configure them if it knows that it's going to run them. Configuration ends up looking something like this. You want it to be as lazy as possible, and that's really important for performance. And lastly, there's a few different types of common tasks. The most minimal one is this default task, which is just an empty shell, hey, this is going to do something. But there's also other common ones like source tasks, which take in a collection of source files, compile tasks, which have a class path notion in them. And Gradle projects are effectively just sort of like a DAG of tasks that it needs to execute along the way. So next we have projects. Projects contain a set of tasks. They can also have other things in them, like source sets. They can have subprojects, and every directory in between, even if it doesn't have a build file, is also technically a project. And they can have plugins applied to them. So it's really just plugin or projects all the way down. Plugins are basically reusable bits of Gradle configuration logic. They can be applied to projects. And there's some well-known examples out there that you're probably familiar with, like the Android Gradle plugin, or AGP for the rest of this talk, Kotlin Gradle plugin, KGP. There's a bunch of first-party ones from Gradle, like Java, Java Library, Application. Some of these you've probably seen before. And we also open source ours, called Slack Gradle plugin, or SGP, very original naming here. And I'm going to actually link a few examples from this throughout the rest of the talk, too. And then this ends up living in your plugins DSL at the top of your build files. Next, we have configurations. Configurations are essentially just named collections of files. You're probably most familiar with these from like the implementation, test implementation, API configurations that you're using for your dependencies blocks. But Gradle ends up actually passing quite a bit of information around through configurations. So it's really just configurations all the way down. You can kind of see a pattern here. Next, we have configuration. Different than configurations, this is the time that Gradle spends sort of thinking about what to do. So you hit go on the command line. It sits there configuring, possibly longer than you would like it to, and eventually tasks start running at the end. And the time between when you hit go and when the first task hits the road is this sort of space at the beginning. This is also a build scan. We're going to have a few of these in the rest of the talk. This gives you a nice timeline overview of what's happening. It's great because Gradle doesn't really know what happens in configuration, so it just says that something happened here. Configuration caching is a new feature we'll talk about as well, that hopefully is the goal is to try to eliminate this for most of your builds. Next, let's touch on caching and incremental builds. So there's sort of multiple layers to this, and Armis Liutikas, I hope I pronounced that right, wrote a blog post about this quite recently. It was pretty good, and definitely recommend checking it out. There's multiple different levels of caching within Gradle. You've got your build directory, which is used by really whatever tasks decide to put in there. It's sort of a dumping ground. Caps store stuff there, Kotlin store stuff there. Gradle itself also retains some in-memory caching for like task snapshots. Then we've got your actual like build cache. There's going to be a local one on your machine. You can also have a remote build cache that your team has maybe set up on a server. You've got your configuration cache, which we're going to talk about more later, but this is that cache for configuration time. We've got the Gradle user home directory, which for most people is just like the home.gradle directory, and this is where Gradle stores a bunch of, we'll say, like reusable, non-project specific stuff. So like it'd be really annoying if you downloaded a new Gradle wrapper every time you cloned a different project, even if they were the same version. So Gradle caches these in there. And not studio caches. So this is something that I end up seeing a lot, where people will be like, hey, my build wasn't working, so I hit invalidate caches and restarted, and then nothing helped. And I really want to emphasize this. This is never going to fix your build. Like, not once. It might like appear to, like you maybe have like a run configuration that's broken, and so like you do this, and you're like, oh, my build is fixed. And it's like, it's not quite the same. Please don't think that this fixes your build. It's never going to fix your build. This fixes IDE issues like, maybe a Gradle sync went wrong or something. But if you're like running a compilation, the compilation fails, and you're like, I think that this is something wrong with Gradle, this is not going to fix it. Next, we've got incremental compilation. Again, there's multiple kinds here. The ones relevant to this audience are going to be mostly just Java and Kotlin. Java's is by Gradle. It's built into Gradle itself, lives in the Java compiled task. Kotlin's is implemented by JetBrains, and more recently with a lot of contributions from the Google compilers team, or AGP team, one of those two. This is a little bit different in caching in the sense that this basically recognizes, hey, like we need to run the compilation task again, but let's try to run it as like fast and minimally as possible. So there's sort of two aspects of this. There's full compilation avoidance, which is to say, like, hey, can we just avoid running the compilation entirely? This is obviously the ideal case. This is usually done based on what's called an ABI, or an application binary interface. You can think of this as sort of like a public API. So if you say, change a method to add a print line to it, and nothing else has changed, then theoretically, everything that depends on that doesn't need to recompile because no signatures have changed. And this is how the Java compilation avoidance in Gradle itself works. For incremental compilation, which is, say, we've changed the signature for something, then it's going to try to intelligently look at it and say, hey, like, can we recompile just like one file? Like, is there only one usage? Can we just recompile that? You know, something to try to minimize the amount of work being done. Kotlin's is fun because it works differently. So it actually has no compilation avoidance currently. It's incremental only, but there is some good news coming soon. So encouragement to stay till the end of my talk. This depends on a mechanism called producer side incremental compilation data. I'm just going to start saying IC for the rest of the talk. It's a lot of syllables, and we don't have much time. So this makes it tricky, and this is where actually a lot of issues in builds that we run into today come up in. So we kind of think of a compilation like this. You've got like project A, project B depends on project A, and we run with it. A more realistic diagram ends up looking a little like this, where project A produces this sort of intermediary IC data binary, and then project B consumes that. So what this means is that project B depends entirely on project A telling it what's your current incremental compilation state, and based on that decides what it needs to compile. And this is produced entirely by Kotlin C. Now, this comes with problems, because it means that if Kotlin C didn't run, then it has no IC data to run with, and it's just going to do a full recompilation every time. So if project A is a pure Java project, if it's a resources-only project, you know, view bindings being generated, or an r.class files being, or sorry, r.jar is being generated, then you get no IC data, so your Kotlin project is basically going to say, well, I guess we'll just recompile everything. And then if that recompiled everything, everything that depends on that transitively also gets stuck in this process. This happens way more often than you think. We'll cover it a little bit more later. It's also worth explaining a little bit more about these common subtasks. Not all these run, but these probably will look familiar if you worked in an Android project in the past 8 years. These occur in sort of 3 specific cases. So capt is this first case. Capt has 2 tasks. The first one is generate stubs, which is perhaps surprisingly a Kotlin compile task, but it's taking Kotlin sources and generating Java files, which is crazy. So it makes a lot of sense, but it's a lot. So the capt task then takes those Java files and plumbs them all into Java C, which is, so now you've run 2 compilers in your first phase, and you haven't even gotten to the real compilation task. So compile Kotlin is the core sort of compilation task. This is running Kotlin C under the hood, reads in Kotlin files, compiles them, generates IC data, et cetera, et cetera. And then finally, this compile Java. If you have mixed sources, or if you have an annotation processor like Dagger that generates Java, then this task will get piggybacked onto the end as well. And these all have to end up running sequentially, too. So you've got sort of like a 4-stage pipeline in this worst-case scenario. And I'm going to, later in the talk, show a scarier version of this. So you can see how these all start to add up as well. Touching briefly a little bit on this compile Kotlin task. This itself is implemented as a Kotlin compile task, so not confusing naming at all. It, under the hood, is calling through to Kotlin C. Kotlin C is the actual Kotlin compiler. This has its own internal pipeline that consists of essentially just a front end and a back end. The front end you can think of as sort of handling all the like parsing, loading into PSI. If you've ever written a custom lint or something for detect or something, this is where a lot of that infrastructure lives. And then there's an analysis handler API that sits at the very end of that that says, hey, like if I have an analysis handler, I'm going to give it all of the Kotlin files that I've parsed, and they can do whatever they want. And that's where like capt and KSP, parts of Anvil, the compiler plugin, live in. And then it hands all this off to the backend, which has an IR layer, which is an intermediate representation that then can be lowered into different supported platforms. So JVM, native, JS, etc. IR is where a lot of other compiler plugins live, so like Kotlin X serialization, Parcelize, what have you. Amanda Hinchman Dominguez has a great series started that explores this in more detail if you're interested. So in our previous tasks, these kind of run different parts of this pipeline. So generate stubs runs just the front end. It says, you know, hey, I'm I'm just interested in knowing what the Kotlin files look like. You don't need to compile anything else after that, so it just disables the backend and runs only the front. Capt runs none of this, it runs Java-C. Kotlin compile runs all of this, and then finally, compile Java obviously doesn't run any of this again. So I think it's enough context for Kotlin C. Last two we'll touch on quickly. We've got two different types of daemons. The Kotlin daemon is used by Kotlin compilations and Capt, and the Gradle daemon is used by basically everything else. It's useful to know because you can actually tune their arguments differently, and we're going to talk a little more about that later. Lastly, worth touching on, annotation processing. There's sort of two canonical implementations now that you could use. One is the traditional Java-C/Capt pipeline. Java-C, remember, as we just talked about, is actually just what Capt is running under the hood. It's just sort of taking Kotlin files and saying, hey, just pretend these are Java, because we didn't want to rewrite this ourselves. So they can run non-incrementally. They preferably should run incrementally. Capt is actually pretty good about warning you if you're running any processors non-incrementally these days. There's two types of incrementalism themselves. There's isolating and aggregating. I'm kind of skipping through some of this for time, but isolating is basically the ideal case. It's the faster one. It's sort of a one-to-one mapping of source files to generated ones. Aggregating is slower because you'll have multiple source files getting referenced by one final generated file. And this can break easily. So like in Dagger, for instance, anywhere that you have like an injected type, you need to run the Dagger processor over it to generate Dagger factory for it. And if you try to use that in some sort of downstream module and there's no factory for it, then Dagger is going to generate that factory in the downstream one, and that actually ends up breaking incremental processing. And so it's a huge sort of like foot gun to easily run into. That, I think, covers everything I want to touch on for Gradle. So now, hopefully, you know a little more about Gradle, you know a little bit more about Kotlin C, and now we get on to the fun parts and talking about how to make things faster. So it's going to be in three general areas. First is going to be things that are hurting your build today. These are going to be things that you're possibly doing today that are just sort of the wrong thing to do, and that you should fix. You should treat them basically as bugs. Next are going to be things that will improve your build. These are things that are not necessarily wrong to not do, but things that would definitely help. And some of these are going to be more involved than others to try to implement. And the last thing is going to be things that will keep your build fast. And this is longer-term investments, tooling, telemetry, et cetera, that you can basically come to rely on to make sure that your build quality doesn't regress over time. So, things that are hurting your build today. First up, we have the age-old problem, annotation processors. So who here uses Capt somewhere in their build? All right, so basically the entire room. Keep your hand up if you're using Dagger. All right, so still basically most of the room. Yeah, so I'm not going to sit here and pretend like the right solution is to just like remove annotation processors somehow. Like they're kind of inevitable in these larger projects, and it's, you know, we need to work with the world that we live in, not the world that we want. So I do want to take a second to really, really emphasize how heavyweight Capt is. So as we covered before, there's sort of 3 minimum tasks that run in a Capt-enabled pipeline. 4 if you end up generating Java sources. Capt is really brittle to class path changes. So if you have something upstream that is, you know, getting recompiled, or even just like jar ordering changes, like Capt will just say, oh, cool, okay, I guess I'll just rerun everything again. You know, I wasn't doing anything anyway. So, yeah, you'd be really surprised how often it runs. It also is going to be disabling the new Kotlin frontend whenever it runs, which is also obviously not ideal. We're going to talk a little bit about the new compiler later. And it keeps appearing in later problems. So, remember this diagram that we just went through before? We can actually stretch this out a little bit. So stubgen takes in Kotlin files, generates Java files, pipe it into Capt, which is then running Java-C. Then we take all of that, plumb it into compile Kotlin, which is now running Kotlin C again. And then finally, compile Java at the end. I'm really running out of slide space to show this. And you multiply this by every project that you have in your build, and it's going to be a lot. Like, it's not that any particular part of the Capt pipeline is itself slow. It's just there's a lot going on in there. And so there's ways that we can mitigate this. So 4 big-ish ones that I want to cover today. The first one you've probably heard of by now is KSP. KSP is an alternative Kotlin annotation processing tool. I'm not going to spend much time explaining like how KSP works and what it does, but what you need to know is basically that it takes this build graph and simplifies it down to this. If you can remove Java files entirely, it gets even better. Now you're just down to 2. Now, this is probably the realistic best case for most situations. There is interest in making KSP run like in the same Kotlin compile task, so it could potentially be better in the future. But for now, this is sort of like the happy place. For number 3, which means that I've lost a number 2 in here, so it might just be 3 things. Some annotation processing can be done via IR compiler plugin, which runs solely in the Kotlin C backend. This is where, like I mentioned before, a lot of other annotation-based tools run. So a lot of Kotlin's first-party plugins like All Open, Parcelize, Serialization, Moshi X, which is a plug of my own library that has a compiler plugin for Moshi. You can check out this blog post by Brian Norm if you're interested in learning how to write your own plugins. This brings the pipeline down to just 1. And the 4th, but technically I guess 3rd case, is Dagger. So Dagger puts us back at this, sort of the worst case scenario, and as we just covered, everybody in the room here is apparently doing this. So Dagger is really ubiquitous in a lot of projects, and you also, as I mentioned earlier, need to run it everywhere that you have injections, not just every project that you have, say, components. So Dagger today doesn't support KSP. They're working on it. And it still generates Java. So you really get the worst case here. It's a big headache. But in comes this neat project from Square, which is a recurring theme in the Android community, called Anvil. So Anvil does a lot of things. You can go read about it on the repo. But for this case, it has this very specific magic utility called factory generation. This hooks into the same front-end analysis handler extensions that capt and KSP does, and it generates all these factories, and it generates them in Kotlin. So you don't end up with a mixed source set. It generates what Dagger is basically looking for in downstream modules. And it basically kind of runs in and gobbles up all those tasks and leaves you with just 1 task again. It's a free win, basically. It's really, really good, even if you don't use any other Anvil features. But Anvil does have a lot of other features, so you should go check those out too. It doesn't work with components, though, so this pattern kind of relies on isolating out components into like very specific parts of your code base. But it's good. So next, let's talk about build source. Who here uses build source in their projects? All right. I'm guessing most people are using it for like either a convention plugin internally or like for hosting dependencies. And it's a huge, huge negative impact. It sort of regularly invalidates your build class path. Anytime you make a change, it recompiles, and then your build class path says, well, our environment has changed. I guess we'll just rerun everything. Like, it's literally like running rerun tasks randomly whenever you're least expecting it. And there's better alternatives for at least those 2 cases that I mentioned. So for dependencies, you have version catalogs, which is a newer Gradle feature that will let you put it all in a nice TOML format. And for convention plugins, you could just put them in a separate repo and upload artifacts to like an internal artifact tree. It's a really significant difference. We moved away from using build source at Slack about a year and a half ago or so, and we've never looked back on it. Some people raise the question of like, what about live testing? It is nice that you can make a change in build source and then like start using it immediately. And for that, Gradle has a solution called included builds, where we have this neat little snippet where we can basically point a Gradle property at the local path for our separate repo, and it will just load that and build it, and we can do all of our testing that way. Next, let's talk about cleaning. Who here runs this command? Like weekly, monthly, daily? Stop it. Just stop. Like, get help. No, don't do this. It rarely helps. If it's a bad cache entry, then like cleaning's not going to do anything because it's still sitting in your cache. You're going to build again after, non-incrementally, wait a long time, and then it's going to come back and say, hey, I've still got the bad cache entry. Like, if you really think it's a bad cache entry, you should be running with like -- rerun tasks. But even that, I think most of the time ends up being like a placebo effect. And what this does, though, is it blows away all of that incremental compilation data that we were talking about earlier. So this puts you at minimum 2 builds away from your next actual like incremental compilation. This is the part where I would maybe, if I was braver, ask the audience to repeat after me, but I won't. So next one that I want to talk about is don't mix IDE and command line builds. So one thing that I see a lot is people will be like building in Android Studio, they're connected to a device, they hit run, make some changes, run, and then maybe they'll, for some reason, switch to terminal, run a different build there. And then all of a sudden, the build in the terminal is slow, and they're like, well, that's weird. And they go back to Studio, and then that build is slow, and they're like, oh my god, everything's going crazy. So the reason that this happens is because Studio is actually injecting different properties into your build based on the device that you're connected to. So you might have, your fancy, Pixel 6 with API 31 on it, and Studio is going to look at that and say, oh, we can actually do a faster build here because you are using a higher SDK device. So we'll just inject a new min SDK for you, which, if you're just sitting in Studio the whole time, maybe that's a win. But if you switch back and forth, all of a sudden, say your command line build, which doesn't have this connection with the device, is going to say, hey, well, the last build was a completely different min SDK. So now we're building with the lower min SDK again, and now we need to run all of library desugaring, and none of it's in the build cache. So basically, I'm not saying like don't build from the IDE or don't build from the command line, but don't switch back and forth between them during your like day-to-day development. Yeah, and Google is reconsidering whether or not this is actually adding much value. So if you want to follow along, you can follow this issue. Next, let's talk about this button. Who clicks this button? Who doesn't know what this button is? Okay, so this is like the build button in Studio. I saw one person raise their hand at the end of that, and you were living in a blissful life. So basically, this is, I call like the I'm feeling lucky button. So this button, its behavior changes. It's dependent entirely on what the IDE thinks you have focused at the time that you click it. So if you have, say, like a source file open that you're editing, it's going to build that module. If you have clicked something in the project navigator, even if you have a source file from a different project open, it's going to build whatever you clicked in the project navigator. And if you have nothing focused, it's just going to build everything. Like it sends a command just like Gradle W assemble and just like takes off Avenger style on it. And it's not a good idea. And we actually have tasks that run in our build that basically check to see, like, hey, did they try to run Gradle W assemble and just build everything under the sun? No, we're just going to error immediately and say, this is not what you meant to do. Next, quick comment on NDK projects. Anybody here use the NDK? All right, so like 4 of you. So it'll be brief. NDK is a bit of a spooky, upside-down place. And it makes Studio behave sort of weird and funny. There's some non-cacheable tasks in it too, which are not great. Whenever you're connected to a device and Studio pops up with this like dual debugger, and it's like, which debugger do you want to use? And people are like, I don't know what's happening. So just, if you have an NDK project, stick it in another repo, stick it on your Artifactory. I think it's the 3rd time I mentioned Artifactory. You should get an internal Artifactory. It's really useful to just punt the really awkward artifacts onto that and not think about it. Next, let's talk about APIs in Gradle. Gradle has a really big, this is the one that I'll get an angry tweet about this later. Gradle has a really large API surface area. A lot of it has improved dramatically over the years, but a lot of it is also really error prone and like sort of a landmine to step in. So what you should try to do is basically audit eager APIs in Gradle. So these are things like configurations.all, anything using like getters, creating a new task rather than registering one lazily, properties that are sort of hard-coded values rather than using Gradle's property APIs. Tony Robulik just wrote a blog post about this like 2 days ago. He sent it to me. I was like, this is great. Can you publish it by like Monday night? So I would just run through this blog post and audit all the things that he mentions in there. These cover most of the common footguns that you kind of see in this. The APIs themselves, they're not wrong. Like Gradle won't deprecate them because there are correct times to use it. Much, I guess, in the same way if you're in a, never mind. So next, let's talk about incremental compilation issues. So I wrote a longer, detailed post about this last summer. It's a little bit out of date now, but some of these are still relevant today. So as I mentioned earlier, incremental compilation can be broken in surprising ways in Kotlin. To cover some of those common ones, like I mentioned before, Java projects regularly break IC because they don't generate IC data. So if you have a pure Java project anywhere in your repo, anything that depends on it and all the things that depend on that are not getting incremental compilation. And there's a really easy fix for this, which is just go and add one Kotlin file. You can make it a private abstract class that no one can make an instance of. But just having that present will absolve you of this issue. Next, sometimes an issue that comes up is code generation tools will generate non-deterministic inputs. SQLite, for instance, had a recent issue around this that was fixed in their upcoming 2.0 release. This is something that you don't really notice unless you go like hunting for these in build scans. You're like, why is this running? But it is something that whenever it comes up, usually the maintainers are pretty quick to respond to it when you file a bug report. Lastly, also, resource API changes. So remember we were talking before about like basically you want to use the API as your input for incremental compilation. Kotlin does this to some extent in its own IC, and with resources, they're like constants. And so if you change the value, the like public API is changed. And so this ends up breaking incremental compilation whenever you make just like a resource value change. And finally, cleaning. We touched on this before. Please stop cleaning. It's really bad. It's the only context where I feel like I can really say that. Next, let's talk about task issues. These can be a little bit sort of nebulous because basically it boils down to this question of like, why did this run? Note that this kind of requires using build scans. You can write your own tracing for this, but I'm not giving a talk about how to write your own tracing for Gradle. There's sort of two parts to this. So the first is identifying task issues. Now this part is sort of straightforward. So say your like canonical like build the app command is just app assemble debug. So you do one build, bunch of tasks run. Now you run it again, and ideally no tasks have run. Like this is like the happy path. Everything is sort of up to date correctly. You're good to go. If for some reason tasks did run, then like you've got a problem here. So sorry, I should mention like this is without caching enabled. So purely just Gradle's like in-memory implementation for this. So if you have tasks that are still running, even in this case, that's like really bad. That means you have something that is just not doing like up-to-date checks correctly. Sometimes they're simple to diagnose. You can go look at the build scan and it just says like, hey, like they said they're up-to-date, never. And that's an easy, well, hopefully easy fix. But yeah, these are bad. And these can also come up, say, for a source task because something has changed about the input files. If you change no files and it's saying, hey, the input files changed, then like you've got some ghosts in the machine you need to figure out. This is also where build scans become really useful because you can actually compare two builds and see exactly which properties were different and know where to look. Gradle will tell you that they're different, but they won't tell you what the values were, so it's like almost useful. So let's say now that you've fixed this case, the next is identifying caching issues. So for this, we use the same test, but now we'll go and enable caching. You build it once, and then you populate the cache, and then you clean it. So I know I just said never clean, but for the purposes of this test, you've got the green light. So clean it once, remove all the local data, and then build again. And ideally, it's all green. And in this case, it should have been pulling everything from your local build cache. If it's green, sorry, not if it's green. If it's green and no new tasks ran, that means caching is working. If any did run, then that very likely means that they're just not cacheable. So remember how I mentioned at the beginning, caching for tasks is an opt-in thing. Sometimes plugin authors just forget that. You can fix those tasks if you wrote them, or you can file issues on the plugin if you didn't write them. Very rarely encounter tasks that aren't cacheable that also shouldn't be like one-offs, like a download task or something like that. Two more variations of this test. One with caching enabled again, but this time we're going to clone our repo into a separate directory, and then we're going to run the build there. And again, we should be able to run this. Everything runs, no tasks, or sorry, everything finishes fine and no tasks run. If any tasks did run, then this is usually a sign that you have some task that's using absolute paths for their file inputs. And those are also really common because, again, in Gradle's API, you have to opt into normalizing paths for this. If any ran, you can investigate that, use build scans. It's usually pretty quick to diagnose which one. And the final version of this test is to run the first build on, if you have a remote build cache, the final version of this test is to run the first build on CI, and then run your second build locally, and that makes sure that you're getting good remote build cache fidelity, especially because you're probably pushing to this remote cache from CI. So if this doesn't work, then you're not really getting what you paid for on this. So yeah. Next thing I want to touch on very briefly is corporate bloatware. So everybody here, has probably worked at a company that has some sort of antivirus software running, and these things they're the worst. They often will hook into kernel task. They run as kernel extensions. They hook into every single file system operation, and it turns out that it's really slow if you have a build system that's got thousands of intermediate files being written and read back along the way. You have this queue of thousands of files. Oh, let me check it. Okay, you're good. And then do that thousands of times. It ends up actually on Intel Macs being a really, really big issue because the processor starts heating up, it starts going into thermal throttling. It's really bad. We're going to talk about modularization later with a fun story on that. The last one is literally just sometimes there's bugs. Like I said, IC can be broken in surprising ways in Kotlin. There are known bugs tracking this that they are working on. And like I said, I mentioned this in that blog post, but Kotlin build cache entries often end up breaking incremental compilation, so that's sort of a weird, the one thing that's supposed to help is breaking the other thing that's supposed to help. Gradle's abstract compile task, which a lot of other tasks extend from at some point, is sensitive to class path jar ordering, so you could have two different jars that have completely exclusive classes in them, but if the order of them changes, then Gradle will be it's out of date, we must rerun. And we don't really know what causes this. And there's some also awkward APIs in KGP, like this free compiler args, that if you've ever used, say, an experimental API, you have to add something to this, and you have to do a plus equals on it, and then it says it's suspicious, and it's weird. So they're going to fix that, hopefully in 1.7. So the last one that I want to mention here is old tools. So who's still using JDK 8? All right, good, all right, 2 of you. Do you know that it reached end of life 100 years ago? Okay, cool. So yeah, JDK 11 is what the default is for most of the Android tool chain, but JDK 18 is the actual latest one. We are currently on JDK 17 at Slack. We're still targeting JDK 8 bytecode, but at the end of the day, you want to use the latest tool chain that you have available to you. So just update your stuff. There's a lot of different things that affect your build class path that you don't want to be using old versions of this. So you've got your JDK, you've got your Kotlin versions, Gradle versions, any Gradle plugins, compiler plugins, etc. And once you're on these newer JDKs, you can actually start doing some pretty neat things. So you can pass in custom JVM arguments. You can tune your garbage collector. So we actually found that the G1 garbage collector, which is the default in newer JDKs, is actually faster, but we can actually tune it even further to give more space to the young generation zone or region of its heap. Gradle is a bunch of short-lived tasks, so giving it more space for short-lived objects turned out to actually help about 5%, I think, when we measured it. You can also tune the daemons differently. So our build is dominated by Kotlin compilations, so we just give more memory to the Kotlin daemon than the Gradle daemon. I'm going to skip over this part because we're short on time. So basically, don't merge main on CI builds first. I don't know if people often do this, but Slack did this when I joined. Lint uses a lot of memory, not a surprise. But if you really want to fix this, you need to give it more meta space. I'm not going to explain what meta space is, just that it's a thing. Tune your daemons on CI. You can tune them differently there. So if you have, say, lint running in one work stream and everything else runs in different ones, you can give the Gradle daemon more memory on that one only and prefer the Kotlin daemon everywhere else. And one more fun one. Who uses code coverage? All right. I look forward to your letters. Basically, we found very little benefit with code coverage, and also removing it gave us back 10 minutes on CI. So maybe cover, like with a K, the new one is better. But yeah, so that's it for things hurting your build today. Next, let's go through things that will improve your build. This part's going to be a little faster and shorter on the details, because these are more sort of off-the-shelf solutions you can take on. So first of all, build caching. Did you know this is not enabled by default in Gradle? If you didn't, this is an easy one-liner to go and add into your code base today. So go turn that on. Remote build caching is the next level of that. You can build your own. You can also get this on Gradle Enterprise, where it's built in. Next, let's talk about build cache issues. So sometimes there's bugs, like I mentioned before. Oftentimes they happen in AGP. And AGP is pretty quick to fix them in their main branch. But AGP spends about 300 years in alpha. So the next best option for you is a plugin like this Android Cache Fix Gradle plugin that will just go in and retroactively apply fixes for these in your build. It's sort of a free win. Apply the plugin. Don't think about it. Sorry, you should think about it, but you don't have to think about it very much. So next is virtual file system. I think this is enabled by default now in Gradle, but it's a newer feature that will use a virtual file system. It makes it easier for Gradle to more performantly track file changes. You get faster task snapshotting, similar to Watchman if you've ever used Buck. Next is configuration caching. This is an even newer Gradle feature. This caches configuration time. It's still incubating, but we're using it at Slack, and it's saving us about 30 to 45 seconds of build once the cache is warm. It also will potentially significantly reduce your memory footprint because you're skipping configuration. So if you're doing configuration, you have to load all that in memory, and it kind of sits there forever. If you're not doing it, that's another nice win. You'll probably have to do a little bit of tinkering with this to find any issues. A lot of Gradle plugins in the community have not fully caught up to this yet. Next thing that I want to highlight is this neat little Gradle plugin from the folks over at Dropbox called Focus. It's sort of like Buck Project or Focused projects if you've used Bazel. It's relatively new, but it's pretty clever, and it's something that Gradle, I think, should really offer natively. So the quick and dirty explanation of it is, say you have a repo with 3 apps in it, and you're only working on one app. And it would be really a waste of resources if Studio was indexing everything else in your project as well. So you can take Focus and say, hey, focus this project. And this plugin will go in, figure out all of its dependent projects, and then create a settings file that is only those project dependencies. So you only basically index a slice of the actual repo. If you have a lot of sample apps in your repo as well, this can really shine there. Next one, single variant libraries. So by default, Android projects get a debug and a release variant. 99% of our libraries, though, are just source main and nothing else. So it's sort of silly to have double the overhead. So we just remove it, and we say, hey, if it's my code sample is wrong here. We only have the release variant enabled, and we disable the debug one. This is easy enough to do. You do it once. Every project gets it for free after that. Next, modularization. No secret that modularization is sort of widely considered to be the most effective way to improve your build times, but it's also a lot of work to do. So definitely not the easiest one. You have to plan for it well. You need to get wider buy-in. But once you do it, aside from better parallelization, it's also easier to isolate known slow things. So like I said before, you can't fully ever escape capped in some cases, but you can at least put it in very small, hidden away parts of your repo. It has costs, though. So on Intel Macs, we increased our parallelization to such a point where thermal throttling would kick in all the time and actually ended up slowing down our builds. And so I know I said in my talk description that you don't need nice new hardware to make your builds faster, but it does help. So it does make a huge difference. We actually saw a 68% improvement in average local build time when moving to the new M1 Max versus the existing top-of-the-line Intel Max that people had. It's also a problem that you can solve with money. It's a known fixed cost, which is really nice in a world of sort of trying to explain well, this will have potential value. We don't know how much, but we think it's worth the investment. This, you can say, it costs this much, and we know it has this benefit. So it's also CrowdStrike proof, which is great working at Slack. So another thing with modularization is that any sort of macro level or like minor changes you make gets you macro level wins, because you can make that change in one project and it gets applied to all of them. Oh man, I'm running quick on time here. Okay, so modularization also ends up in sort of combinatorial explosions of things, namely merged R classes. There's a new non-transitive R classes flag that you can use that will disable this. Instead, you import it from the host module. We saw actually surprisingly big wins with this. So we shaved off 5.5 megabytes from our APK size, 14% improvement in build times with one particular benchmark. And the pattern for it wasn't too tricky to incorporate in. Another fun thing to do is just disabling Android builds that you're not using. So most of our library projects, like I said, are little worker projects. They don't use build config, res values, render script, any of that. So we just disable them all by default and ask people to opt into them if their project needs it. Next, prefer JVM-only projects if you can. AGP is a heavyweight plugin. It does a lot of work. It sort of has to be by nature, but if you're not using any Android APIs, then it doesn't need to be an Android project. And the last big one is making a platform plugin. So if you've ever worked with a BOM, this is kind of like the Gradle project equivalent of that. And it's the same concept, and it's useful for enforcing the same version across your projects. So we built one that enforces one given a version catalog, which is pretty neat because that's where you're declaring all your dependencies. You can find the implementation for that here. Racing through here to catch up on time. I've got a ghost bullet at the end of this. I don't know what that was supposed to be. Remove Jetifier if you can. There's a new check Jetifier task in AGP 7.1 that you can use to help you with this. Using API and implementation projects is really handy. This is different than API and implementation configurations. Those just hide visibility, but it doesn't hide it from, say, like recompiling or from your class path. And API implementation projects break that dependency entirely, rather than trusting Gradle or Kotlin to figure out whether or not it needs to rerun. And finally, things that will keep your build fast. So I'm going to really sprint through this part. So Gradle Enterprise, to be honest, it's kind of required for non-trivial teams, I think. Unlike Bazel and Buck, like Gradle is a product that needs to make money. This is how they do it. But it's also, I think, not that expensive. It's kind of like the M1 Max. Like, it's a dollar value that you can assign to a problem that has like a solution. And it's cheaper than trying to do it yourself. We had an engineer that tried to build tracing, spent an entire quarter on it. It was never going to be as fully featured as Gradle Enterprise, and we spent more, paying his salary that quarter than we spent on Gradle Enterprise for an entire year. And it's quite good too. Remote build cache. It's got build scans, easy to compare builds, get trends, insights, visualization. There's an export API if you want to pipe it into something else. You get information about your critical path in your build. You can slice and dice data differently with tags and custom values. And it's just really handy if people are like, hey, there's something wrong with my build. And they're like, can you send me the build scan? And they're like, yeah, right here. This is really useful for benchmarks and visualizations. So we add special tags to benchmarks, and we run them on a nightly basis. Benchmarks are another thing that you should do to help prevent regressions. This is one of our benchmarks for our top of the level remaining legacy app project, and you can see where we finished up some last minute modularization, which was nice. Another one for making a library change, so this is really deep down in our build. Slowly creeping up with modularization, but we're not too surprised with that. You can also use this to just keep an eye on the general local build times everywhere, which has a lot of variation, but it's also still useful. And this sort of telemetry in general is something that you should really check in on. I think a weekly basis or every couple of weeks, something where you're basically looking at a few fixed numbers that you decided in your team that you care about. And if it changes significantly, then you go in and try to figure out what caused this, and just check in periodically. Selection of other metrics you can track in enterprise scans are is it local versus CI? The system architecture, this was really helpful when we rolled out the M1 Max, because we could basically slice that data differently and see really clearly how much faster they were. Thermals, so I've complained before about thermal throttling being an issue. We have a whole thermals watcher implementation that we wrote for tracking this. Git state, environment information. Another plugin that's really useful is Gradle Doctor, written by Nelson Ozaki. This is a plugin that basically warns and enforces common Gradle configuration mistakes. This includes like if you've got different Java home environment variables set, cache speed issues. If you accidentally try to run like assemble everything under the sun, it will catch you on that as well. Some things you can run in CI so that like running all of your build twice and make sure that the second time nothing else runs. Android X repo actually has a neat implementation of this that you can borrow. Modules Graph Assert is a neat plugin that lets you enforce module visibility. So you can say like, hey, like core library shouldn't depend on features, or maybe you want to say that features shouldn't be able to depend on other features for like better separation. It's a neat plugin, and we enforce this, and we can actually see. Well, this looks better on my laptop than it does here. But you can actually see like clear lines where we have these layers in our build graph, and it's really helpful for enforcing parallelization. Dependency analysis, Android Gradle plugin. It's not actually specific to Android. He regrets putting Android in the name. I've talked to him about it. It's funny. This is written by a guy named Tony Roblick, who I mentioned earlier, and it can analyze your projects for a number of common issues like unused dependencies, wrong API implementation, configurations, unnecessary plugins, and more. What's also neat is it exposes an API that you can hook into where it then feeds in this advice, and you can take that and say automatically remove these unused dependencies from your own files. Next are convention plugins. So I've mentioned our own plugin several times. This is a big convention plugin, and these are plugins that automatically apply certain conventions or standard configurations to a project. So we hoist essentially all of our common configuration logic into this plugin to simplify project setup, defaults, optimal configurations, and allows us to take something like this that's really repetitive and dry it up into something smaller like this. We expose this nice little feature DSL, which is also great for feature developers who don't really want to have to know how to wire these things up correctly. They just say, I want Dagger. I'm like, cool, ask for Dagger, and then you're good to go. We develop ours in the open. README has a bunch of highlights. Definitely please check it out. And then there's also preparing for the future. So this is essential not only to know what's coming in the pipeline, but to make sure that you're ready for it. I'm not going to go too much into patterns here. We've written a blog post about it called Shadow Jobs that you can read more on there. Most of this is also fine just to test manually and ad hoc. There are some highlights that I want to call out real quick. There is a new Kotlin IC implementation coming. It's consumer-side IC based on like the class path that is visible to it rather than depending on upstream modules to produce it for them. There's an unstable preview in 1.6.20 guarded by this Gradle property. You should try it out and report bugs. They are targeting 1.7 for like the official like preview of it, beta, something like that. It will be documented, I think, in 1.7. Solves almost all of those producer-side issues that we talked about earlier, and it even has true compilation avoidance in some cases. This is a really great detailed write-up from the Googler that contributed this in this issue. Go check it out. And just to really whet your appetite for it, this is an incremental build where we made a change to a core library project, just adding a print line to a function. So it should be like no ABI change. And it took about 3 minutes and 12 seconds. And with a new IC, it took 13 seconds. So this is pretty great. The other big thing on the horizon is the new K2 compiler. This is reaching beta or a preview in Kotlin 1.7, I think. They've promised different build speed improvements. I think the current value is around 2 to 4x improvement. They've also got a blog post and a video in there that you can check out. Configuration caching, I know I mentioned this before, but it's technically still in preview, so I should mention here that like it will be rough around the edges, but it's almost close to being default, I think. And it's important to mention because there is a part 2 to configuration caching called project isolation that is coming down the pipeline. And this is for caching basically like loading of individual like build files. I don't really know too much of the details on it, but the eventual goal of this is that it'll allow parallel configuration and tooling model creation, which means parallel Android Studio Sync, which I think is hopefully the exciting buzzword to throw in there. It's still work in progress, but the current TLDR is like if you use all projects or sub-projects callbacks in Gradle, don't do that. That's not going to work with this. Finally, how can I help, you might be asking. And the good ways to do this are try these things, report bugs eagerly, open source your own build stuff. Like we open sourced ours because like that's not our secret sauce. Like our secret sauce at Slack is like emojis and stuff. Like this is not. And it's really helpful for like public repos of issues. Test and prepare for new features, use those modern Gradle APIs, make your own convention plugin, dry up a lot of your repetitive build logic, and file feature requests. Almost all of them are really receptive to feature requests. I'm not going to say don't file feature requests on Gradle, but you should temper your expectations. What should I go home and do today? Audit those bad APIs doing eager initialization, update your tools like JDK, Gradle, Kotlin, etc. Swap in KSP for capped wherever possible. A lot of processors have KSP implementations now that you may just not be using yet. Make your library single variant, disable Android features by default, and just enable them where you need them. Fix any Java-only projects you have today using or that are breaking incremental compilation. You could wait for the new class path-based one, but why wait for faster builds? And run dependency analysis to remove unused dependencies. Almost done. What should I do tomorrow? Learn some Gradle. Hopefully you've learned a little bit today, but it's it's one of those things where you can do with 20% of the work gets you 80% of the way there for like being able to unblock yourself when you run into issues. Try to reduce and remove like the cap footprint where you can in your build. Create some Gradle profiler scenarios to keep track of things over time. Modularize. Use Gradle Enterprise. Get on Apple Silicon if you use Macs at work. Incorporate new tools prep into your actual like team planning. Like allocate dedicated time for like preparing for these rather than just waiting for them to come out and then being surprised when your build doesn't work with it. And open source your stuff. If you want to follow more people to learn more in this space, this is a great list of a bunch of people. Zav didn't have a website, but he just says, please stop using internal AGP APIs. And that's all I got. Thank you for coming and for staying late.